Welcome to This Explainer. Today, we're diving straight into an absolutely epic saga. We're talking about a story of fire, ice, sheer chance, and survival against pretty staggering odds. We are going to trace the natural history of our entire planet, following its journey from a chaotic cloud of stardust all the way to the incredibly complex, life-harboring world that we get to call home today. So let's just jump right in. 4.54 billion. Take a second and really try to wrap your head around that number. That is the age of the Earth in years. It's a time frame so massive, it honestly kind of defies human comprehension. Just to put that into perspective for you, our planet has been around for roughly 1/3 of the age of the entire universe. And human history, well, that's barely a microscopic blip right at the very, very end of this timeline. So to actually understand how we got here, we've got to rewind all the way back to the beginning. Section 1. Forging the Earth. From stardust to a molten world. To make sense of this immense history, geologists divide the whole thing up into 4 major eons. We kick things off with the Hadean eon. It's named after the Greek underworld Hades. And trust me, it earned that name. It was a completely hellish, molten landscape. Then, around 4.0 billion years ago, things cooled down enough to enter the Archean eon, which is where the very first primitive life actually emerges. After that comes the Proterozoic, meaning early life, starting 2.5 billion years ago. And finally, a mere 538.8 million years ago, we hit the Phanerozoic eon. That translates to visible life, meaning dinosaurs, mammals, and eventually us. Kind of wild to think about, right? Every plant and animal we are familiar with today is squeezed right into that tiny final fraction of Earth's history.
But, back in those early days, you literally wouldn't even recognize this planet. We actually snagged our very first atmosphere directly from the solar nebula. It was just light elements, mostly helium and hydrogen, but the intense heat and harsh solar winds, they blew all of that away pretty quickly. Then, as the molten Earth started releasing gases from extreme volcanic activity, we got our second atmosphere. Now, this one would have been unbelievably toxic to us. It was this heavy, thick mix of greenhouse gases, carbon dioxide, and methane. Looking up, the sky might have even appeared orange through this hazy, methane-rich blanket, kind of like Saturn's moon Titan looks today. And the most crucial detail? There was absolutely zero oxygen. None.
So the air was toxic, but the physical environment? Unimaginably violent. According to what scientists call the giant impact hypothesis, shortly after our proto-Earth formed, it got slammed by another planet-sized body. We're talking something roughly the size of Mars, which researchers named Theia. This was definitely not a minor cosmic fender bender. This collision unleashed about 100 million times more energy than the asteroid that eventually took out the dinosaurs. It literally vaporized chunks of Earth's outer layers, blasting a massive ring of molten debris straight into orbit. Over just a few weeks, driven by the force of gravity, all that debris clumped together to form our moon. So yeah, the very existence of the moon in our night sky is the direct result of a catastrophic planetary collision. Section 2. The Spark of Life. Against all odds. Which brings us to a huge mystery. How did life actually emerge against such impossible odds? As the Earth moved into the Archean eon, it finally started to cool. That initial crust solidified, and water, which was largely delivered by comets and meteorites, began pooling to form vast oceans. And somewhere, somehow, in that primordial soup, non-living chemistry just woke up. It became alive. Now, how exactly did that happen? Well, full disclosure, there's no single scientific consensus on this yet, but we do have several really compelling theories. First up is the RNA world hypothesis, which suggests that self-replicating RNA molecules, think of them as simpler single-stranded versions of DNA, were the first things to form. Then you have the iron-sulfur world theory. This one proposes that life actually kicked off as chemical reactions deep underwater, right next to boiling hydrothermal vents, using iron and nickel sulfides as catalysts. There's also the lipid world theory, arguing that double-walled fat bubbles formed first, basically acting as tiny, empty containers that eventually trapped the right chemicals to build a cell. And finally, my personal favorite, the clay theory. This fascinating idea suggests that the rigid crystalline patterns found in natural clay actually acted as the very first templates, stacking and assembling organic molecules. But look, whichever theory turns out to hit the nail on the head, the takeaway is the same. From absolute chemical chaos, a survivor emerged. And out of all those early microscopic protocells, it seems only one specific lineage managed to survive and pass on its genetic code. Scientists call it LUCA, the last universal common ancestor. Floating around roughly 3.5 billion years ago, this microscopic single-celled organism is literally the great-grandparent of every single living thing on Earth today. The trees outside, the birds, the fish in the ocean, and yes, you watching this right now. You are directly related to this tough little survivor from the Archean. Section 3. The Oxygen Revolution, a breath of fresh air. So, that resilient life, it didn't just passively exist. It actually started to change the planet itself. For a really long time, early life basically just snacked on the chemical environment around it. But then, this massive evolutionary leap happened. Early organisms, like cyanobacteria, evolved photosynthesis. They literally figured out how to capture energy directly from the sun, tearing hydrogen away from water molecules to create sugars for fuel. But this incredibly clever process came with a catch. It produced a highly reactive waste product, oxygen. Just by living and pumping out oxygen as a waste product, these microscopic bacteria completely re-engineered the chemistry of the entire planet. They effectively built the third and current of Earth's atmospheres, the exact one you and I are breathing right now. Now, ironically, this new oxygen-rich air was basically poison to a lot of the older anaerobic life that existed back then. It even triggered severe global ice ages, these terrifying eras we call snowball Earth, by essentially eating away the planet's methane greenhouse blanket. But in the grand scheme of things, this oxygen revolution was absolutely crucial. It paved the way for larger, more energetic, complex, multicellular life to finally evolve.
Section 4. The 5 Mass Extinctions, the Great Resets.
Now, as much as we'd love to think the history of complex life was just this peaceful, steady climb to the present day, it wasn't. It's actually punctuated by sudden, violent tragedies. To really grasp this, we need to understand what a mass extinction actually is. You see, extinction itself is just a normal part of the evolutionary engine. There's a natural background rate where species slowly die off and get replaced over time. For example, losing about 65% of species over a sprawling 100 million year period, that's normal. But a mass extinction, that is an entirely different beast. It requires terrifying magnitude combined with incredible speed. We define it as at least 75% of all species on Earth being completely wiped out in less than 2 million years. It is a catastrophic planetary-level reset. And this brings us to a rather grim historical record known as the Big Five. Let's walk through these. First up, the End or Division, 444 million years ago. Severe glacial shifts and tectonic uplift wiped out 86% of life. Next is the Late Devonian, 360 million years ago. Now this is wild. The rapid, explosive growth of early land plants actually triggered immense global cooling, killing off 75% of species. Then the End Permian, 250 million years ago. Unbelievably massive volcanic activity in Siberia sparked runaway global warming and toxic acid rain. The End Triassic follows, 200 million years ago, where 80% of life died off because underwater volcanoes drastically altered the ocean's chemistry. And finally, the one everyone knows, the End Cretaceous, 65 million years ago. A massive asteroid slammed into modern-day Mexico, triggering rapid cooling and erasing 76% of life, including all the non-avian dinosaurs. Take a close look at the suspected causes here. Notice the pattern? Rapid, severe disruptions to the climate and drastic changes to the chemistry of the oceans and the atmosphere. That is the common thread. I actually want to pause and just dwell on the End Permian extinction for a second. 96% of all species were lost. 96%. Those Siberian eruptions pumped so much CO2 and sulfur into the sky that the oceans became highly acidic, and literal acid rain scoured the continents. Life on Earth came within a razor-thin 4% margin of total permanent annihilation. Let that sink in. Every single animal alive today is descended from that tiny, resilient 4% sliver of survivors. Section 5. The Sixth Extinction, a Fragile Balance. So that brings us right up to our current place in this massive geological timeline. Like we talked about at the very beginning, recognizable humans have only been walking this planet for about 2 million years. It's a total blink of an eye. But when we look at the data from the source material regarding the common triggers for past mass extinctions, it's hard to ignore the pattern. Rapid, dramatic shifts in climate, severe changes in ocean composition like acidification, drastic shifts in land chemistry, and massive spikes in greenhouse gases, particularly carbon dioxide. When we map out those historical triggers, a pretty undeniable parallel emerges. The exact same environmental pressures that caused the Earth's most devastating biological resets in the past are the very metrics that are rapidly shifting in our natural world today. It really highlights the sheer fragility of this whole 4.54 billion-year-old system we live in. Now, to be clear, our planet has survived molten fire, cosmic impacts, and freezing ice ages. The Earth as a rock, it will undoubtedly endure. But as we sit back and reflect on the incredibly unlikely chain of events that allowed complex life, that allowed us to thrive, it leaves us with one haunting question to carry forward. Based on those environmental triggers from the deep past, are we currently headed for a sixth mass extinction? And perhaps more importantly, what will our role be in the next chapter of Earth's history? Thank you so much for joining me on this explainer. Keep questioning and keep learning.